Before we get started, I have a quick favor. I've been self-funding the Finding Genius podcast for 5 years now. I've done over 3,000 episodes. And as you can see on YouTube, we're up over 1 million views on the channel, which is fantastic. The next thing I really want to push on is to get up to 10,000 subscribers. Because once we do, we'll be able to put a donate button and we'll be able to solicit donations to help keep the podcast running and to also get the Finding Genius Foundation moving along. We have a big project studying anxiety, depression, and PTSD and working on a product to help people overcome these problems because I've seen them explode recently after the last 2 years of the whole virus situation. So if you would, please subscribe to the podcast. That would help us tremendously. Give us a thumbs up and check in the description for Buy Me a Coffee. It's about $5. If you could buy me a coffee, I'd really appreciate it. It would help keep the channel going, and I love coffee. Thank you. Before we get started, I have a quick favor. I've been self-funding the Finding Genius podcast for 5 years now. I've done over 3,000 episodes. And as you can see on YouTube, we're up over 1 million views on the channel, which is fantastic. The next thing I really want to push on is to get up to 10,000 subscribers. Because once we do, we'll be able to put a donate button and we'll be able to solicit donations to help keep the podcast running and to also get the Finding Genius Foundation moving along. We have a big project studying anxiety, depression, and PTSD and working on a product to help people overcome these problems because I've seen them explode recently after the last 2 years of the whole virus situation. So if you would, please subscribe to the podcast. That would help us tremendously. Give us a thumbs up. And check in the description for Buy Me a Coffee. It's about $5. If you could buy me a coffee, I'd really appreciate it. It would help keep the channel going, and I love coffee. Thank you.
Forget frequently asked questions.
Common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Before we begin, a note from our sponsor. I'm Richard Jacobs, Executive Director of the nonprofit Finding Genius Foundation and host of the Finding Genius Podcast. In late 2016, I was rear-ended at 65 miles an hour by a truck on the highway, which sent me off-road into a ditch. The impact of the collision gave me a concussion and other injuries. At the hospital, a CT scan showed that I had thyroid nodules, which turned out to be cancer. It was then, when I had a biopsy in my neck, that I realized even if I was a millionaire, I wouldn't want a second or a third biopsy due to the pain and the invasiveness of it. And appointments at that time for thyroid experts were 3 to 6 months out. And I was worried about dying now, even if that was irrational. So because of this, I've decided to raise money to conduct a literature review on steroids, on the causes of anxiety and depression, a condition that affects well over 50 million people in the United States and hundreds of millions worldwide. Our goal is to create a codex, a guide that reveals all possible treatments for anxiety and depression for people that live with the condition, or for loved ones that have it, as my wife and my son do. To find out more about our fundraiser, visit findinggeniusfoundation.org and click on Current Initiatives. And now, to our guest.
Hello, this is Richard Jacobs with the Finding Genius Podcast, now part of the Finding Genius Foundation. I have Andrew Mays. He's an associate professor in chemistry at University of East Anglia. We're going to talk about microplastics and nanoplastics. So, Andrew, thanks for coming.
Thank you for having me.
Yeah, if you would, to start out, maybe tell me a bit about your background, and then let's talk about your current research.
Okay, so I started out many years ago as a biochemist. I studied my degree and my PhD in biochemistry, and then I kind of gravitated towards chemistry and towards polymer science. And I spent, in fact, quite a large part of my career making polymers and making, ironically, polymer micro and nanoparticles for various different analytical applications and uses in separation science and so forth. But I was always interested in analytical techniques and in environmental analysis. And that's how I got involved in microplastic research. So about a decade ago, I guess now, when people were starting to discuss the problem and first realized that we had a problem that needed investigating, then I got much more involved in that. And my research really has now moved on so that it's almost entirely in the area of microplastics and microplastic analysis and identification.
Right. So what kind of questions are you trying to answer now with your research?
My particular personal interest is actually in the techniques themselves and trying to develop new methods to detect, count, identify microplastics more quickly, more cheaply, more easily. Because at the moment, the tools we have to do this research are quite restrictive because many of them are very expensive, very complex, very difficult to use. And that really limits the kinds of questions you can ask and the number of samples that you can actually analyze. So I spend a lot of my time trying to develop new approaches, more affordable, more simple, that can be maybe used in developing countries where they don't have such good access to complex, high-tech scientific infrastructure.
Well, how are microplastics isolated from samples that analyze? Let's say I scoop out some ocean water with some microplastics in it. How do I separate them out and see what's in there without destroying them?
Right. Okay. Well, it's actually a really quite complicated question. If your sample's a water sample, you have a reasonable starting point because water in general doesn't have too many solid particles in it. So if you take some ocean water, for instance, it will have some biological materials in it, some maybe small algae or zooplankton, but most of it is just water. So a sample like that you can filter, so you end up with all the solid material on a filter membrane. And you then have the problem that you have to try and recognize the small bits of microplastic in amongst all the other stuff that might be bits of suspended sediment, sand and so forth, or it might be small organisms or fragments of organisms. So usually at that point, you have to do some chemical digestion to try and dissolve away the organic biological materials, but you have to do that quite carefully so that you don't also dissolve and damage the plastic particles, some of which are a little bit, it's possible to also digest some of those. So you have to do that process in a quite subtle way sometimes.
So what does that mean? Like, do people settle out? Like, again, if I have a sample in water, do I let stuff settle? Do I centrifuge it? Like, do I boil the water away and see what's left? Like, the best
normally we filter it through a membrane that has a very small pore size so that we capture all the particles on the surface of a membrane. But you can leave samples to settle and use gravity. And that's actually quite a good technique for some types of plastic, because plastics like polyethylene, polypropylene, they are less dense than water, so they tend to float to the surface, whereas things like sand grains, mineral grains, they're quite dense, so they sink down to the bottom of the sample. So that creates a kind of separation step that allows you to remove some of the things you're not interested in. So that in some cases, that can be quite a useful technique. But mostly we end up, at some point, we end up filtering the samples.
What about charge? Are microplastics, do they tend to be neutral or have a net positive or negative charge? Can you use like a slight electric potential?
It's quite variable. I mean, the polymers themselves in general are not intrinsically charged, but as they sit around in the environment, they tend to get oxidized. So typically old aged microplastics will have a certain amount of negative charge associated with them, but also they tend to have coronas. They have surface layers of other material that just binds to the surface of the particles themselves, and that can actually change their surface properties quite a bit. So it's actually very variable because polymers themselves are very, very variable. There's loads of different types and they all have slightly different chemical properties.
So far, what seems to be the best way to separate out microplastics from samples versus like the most economic way?
Normally, I mean, the way we adopt it in my lab is usually to use some density separation based methods. So we actually use a kind of settling method, but using dense inorganic salts like zinc chloride. So we can increase the density of the aqueous part of the sample. And that helps to make sure that all plastics, and not just really low density ones, that all plastics float to the surface, but that the mineral particles still float to the bottom. So that's a reasonably simple and not very expensive approach. So that allows you to kind of skim off all the particles that you think might be plastic. And mixed with that is also some biological material usually. And once you've got that, you then need to digest it in some way. And there are various different methods. And honest truth, none of them work fantastically well. But the most popular one that we use is simply potassium hydroxide, which is very good at destroying biological material. But unfortunately, it also destroys a certain amount of plastic. Certain particular types of plastics do get eroded by that treatment. So if you have very small particles of those types of plastic, you will lose them because you dissolve them in the process of processing your sample.
Okay. Do you see that some of the methods are destructive to the structures that are formed by the microplastics? Like in water, are any of them hydrophilic? Do they form any complicated aggregate structures?
The microplastics can aggregate together for sure, and they can also mix with a lot of the biological material that is present in the environment to form aggregates. There's not a fantastically large amount known about how that process happens and what consequences it has. Most likely it helps them to sediment out and end up in the bottom sediments of the ocean, even if they are intrinsically less dense and you might expect them to float. In reality, a lot of them end up buried in the sediment, and probably the fact that they're complexing and aggregating with other material in the system is what's helping to kind of carry them down through the water to the bottom of the ocean. But really, there's not a lot understood about that. And again, it's very variable. It depends on the type of polymer you have. So that they will behave in somewhat different ways, most likely, depending on what kind of polymer it's made from, how big it is, what shape it is, and so forth.
Well, is there any non-destructive ways to, send lasers through a sample and see how they bounce off the materials, again, to try to determine the structure? Can you put any in like gas chromatograph where,
okay, it's really, this part is really difficult. There are no simple ways to identify a plastic particle in situ. So you really have to isolate them so you can get individual particles. And at that point, we can use various complex spectroscopy techniques. So we can use infrared spectroscopy, which is quite effective, but is difficult on very small particles. We can use Raman spectroscopy, which is expensive, but quite effective, even on very small particles. But these techniques, these are using instruments that cost £100,000, £200,000 and even more. So, you really have to have very good laboratory infrastructure to be able to use these techniques routinely. In terms of simple techniques, you mentioned chromatography. There are no simple chromatographic methods. Polymers are generally quite difficult to analyze by chromatography. Many polymers are very insoluble in common solvents, so they're really difficult to analyze by chromatography. So there is a way to work out what kind of polymer you've got by chromatography, and that's to use a process called pyrolysis, which basically you heat the material up until you destroy it, and it all breaks down into small molecular components of the original polymer. And you can then separate that mixture by gas chromatography, and it creates a kind of fingerprint of the particular polymer you're looking at. So polystyrene will have a different fingerprint from polypropylene and polyethylene and PET and so on. So you can use that to identify polymer particles. But again, you need some pretty sophisticated analytical equipment to do that. So it's quite a complex technique to set up, and it's quite expensive and quite slow to do it.
So I don't know, what is some of the innovation that you're coming up with or you're working on?
The key technique that we've developed is a very simple method, which is based on adsorbing a fluorescent dye to the surface of the polymer particles. And this kind of makes them light up when you illuminate them under special lighting conditions. So the dye we use is called Nile Red. It's a very well-known fluorescent dye, and it has the property that it sticks to the surface of most types of plastics. And with Nile Red, once it's stuck to the surface of the plastic, if you shine a blue light on it, it makes the particle fluoresce. And it might be sort of greeny yellow, or it might be orange, or it might be red. Depends on the type of plastic you've got and the conditions. But it glows in a particular color. So you can then, if you use an orange filter to block out the blue light that you're shining on the sample, you see the plastic particles kind of glowing in yellow to red colors. And that makes it much easier to spot them and pick them out. Or you can photograph samples after you've stained them in that way. And then you can analyze the photographs and measure and count the fluorescent particles to work out how many particles you've got and what kind of sizes they are. The problem with this technique is that it's not 100% specific. Some things that aren't plastic also stain with this dye. So you're never 100% sure that what you're looking at is really a plastic particle. But the huge advantage of it is that it's very quick and it's very cheap and it's very simple. So you can process lots of samples and you can get a kind of reasonable indication of roughly how much plastic material you think is in the sample. So there's going to be more error than if you use one of the really sophisticated instrumental techniques. But the advantage is that you can do it quickly and cheaply. So this allows you to, for instance, analyze hundreds of samples in order to create a map of an area. So for instance, if you wanted to do, to analyze beach sand from 500 kilometers of beach, you could go and, take a sample every kilometer and create a complete kind of spatial map of the relative microplastic levels in that whole region. If you were using the sophisticated instrumental techniques, that would be an enormously time-consuming and extremely expensive study. But that's a study that, using this simple dye staining method, I could do with a graduate student in a few weeks.
Okay, so who is going to be using these techniques and where and how? Is it already in use? And
this technique is in quite widespread use. It was quite famously used a few years ago in a study done by Professor Sherry Mason at New York Fredonia University, and she studied bottled drinking water, came up with a conclusion: almost all bottled water contains a certain level of microplastics. And this was, I think, very surprising to a lot of people, and it caused major news all around the world and led to the World Health Organization initiating a review to figure out whether the levels of microplastic in drinking water are actually dangerous for people's health. So that's one example where this kind of technique was used. We use it quite routinely in my lab. We analyze lots of marine sediment samples, beach samples, water samples, and so forth. And more recently, I also got some funding to set up a microplastic analysis network in Malaysia. So we built instruments, we trained some people in various labs in how to use this technique, and then we've helped them and assisted them to apply the methods to study various things in their own country. So drinking water, we've been looking at airborne microplastics and so forth.
Okay. So, I mean, is your research primarily in, again, the isolation of microplastics from various environments, or are you also studying other aspects of them?
Mostly we're studying, how much is in various different environments. I'm also quite interested in the polymer chemistry of microplastics, so how they break up, how they weather, how that affects your ability to identify them. So we're getting quite involved in research in that direction to try and understand how they continually break down in the environment and how their fingerprints change as they age and oxidize. What other things are we doing? We've done some work on food materials. We've done some work on fish, looking at microplastics as well, partly just to know how many are in fish, in the guts of fish, but also using that as a kind of marker for how much microplastic is in the environment in which these fish live, because they're picking them up as they swim around and as they feed. So by measuring what the fish accumulate, it's a kind of indicator of how much microplastic is present in the environment in which that fish lives. And you can then compare that data with data from similar fish in other parts of the world and try to figure out, how much microplastic there might be in different environments.
Well, I mean, what can you see about the structure of microplastics in an undisturbed, again, sample of water or sample of air? What happens when they're prepared and, again, taken out of a sample and put in, dried and analyzed under microscope versus being, again, in situ, in the air or in the water? How do they tend to change, or do they not change much at all?
We don't really know, to be honest, how much they might change as a result of the extraction process that we typically use. Quite often we use quite aggressive oxidizing conditions to try and break up the organic material that's, the biological material that might also be present in the samples. So probably that does affect the surface chemistry of the microplastic particles. It's also true that many microplastic particles from the environment are quite fragile. They become quite brittle because of the aging process. And so it's quite possible that some of them break up during the process of isolation. But it's really difficult to know for sure that that's happened because you only see what you have left at the end of the process. So you don't really know if the bits you're looking at were originally one particle that's now become 3 or 20 smaller particles, whether it was already all those small particles in the original sample. So it's very difficult to say for sure, I think. That's all I can say really about that.
No problem. What kind of microplastics so in terms of size, are nanoplastics incredibly difficult to separate versus micro? And then what about fibers versus, let's say oddly shaped pellets or spheres or, what kind of
okay. Fibers are a strange thing because at one level, they're much easier to isolate because they're easy to recognize in samples. So you can actually pick them out manually if you want to. So a fiber is a much easier item to spot in a typical sample than a small irregular particle would be, for instance, because unless the particle is very brightly coloured, it almost certainly just looks like a grain of sand or some other bit of the sample. So it can be really difficult to spot them, and that again is where dye staining can really help you because it allows you to kind of illuminate them and make them more visible. So fibers are at one level easier to deal with because they're easier to recognize, but they're also quite difficult in some ways to handle because they're quite fine and they tend to stick to the surfaces of the glassware and the equipment that you're using. So unless you're very careful in the way you do your isolation, it's quite easy to lose fibers along the way in the isolation process. When it comes to nanoplastics, you're in a really difficult territory because there are really very few effective ways of identifying them with accuracy and certainty. So it's not impossible to do, but it's really, really challenging. And even most of the spectroscopic techniques that we use on microplastics are no longer applicable to nanoplastics because they're simply too small to see for fundamental physical reasons. They're much smaller than the wavelengths of the light you're using to analyze them, and it becomes really, really problematic. So there are a couple of mass spectrometry based approaches that are used to analyze nanoplastics. You may be able to see them. Well, you can physically see them under scanning electron microscopes, for instance. But again, it's not easy to identify that it's certainly a plastic because the analytical tools you have at your disposal alongside the visual image in an electron microscope are quite limited. So whether it's a plastic or some other piece of organic material that looks similar, it's very difficult to tell just from the image and the limited analytical data you can get.
Okay.
So bottom line is we desperately need some really cool new methods for nano scale plastics, and there are some emerging techniques, again based on dye staining, perhaps using multiple different dyes to try and get better specificity, and coupling that with, for instance, flow cytometry or fluorescence activated sorting, so that you can try to isolate samples that have these tiny particles in, and then apply other techniques to them. But it's a really, really tough area. And I think, there are many methods you could use that allow you to definitively identify a plastic nanoparticle, or maybe even a few, if you're prepared to spend some days on it and you have the right kind of analytical instrumentation. But to turn that into a method that you could apply to a sample of soil from a field, for instance, that's a completely different world. And that's an enormously complicated problem that we don't have a good solution to at the moment.
What do you expect is possible in the next couple of years with, again, your methods of analysis, or in general, what do you think will be able to find out?
I hope that using the kind of simple methods that we're trying to develop, we'll be able to make them more specific and more selective by clever use of multiple dyes to stain different types of material in different ways, and then using slightly more sophisticated optical detection methods. So I think that will improve our ability to be sure they're plastic. I would like to think we will get much faster, much more efficient instrumental methods that can scan our samples much more quickly. And that is coming through from instrument manufacturers now. The problem is just the expense. So now we've just bought a very nice new Raman microscope that has lots of automated particle recognition technology, automated sample analysis technology, so it can measure a spectrum, feed it into a database, identify what it is, tabulate all the results. So in principle, at least, these types of instruments can do a lot of analysis unattended, pretty much automatically. But that's the theory. The reality is it still takes quite a bit of effort to prepare the samples nicely to make them good enough that the instrument has a chance of really doing that. It's one thing to demonstrate it on a nice model sample where you prepare some microplastics out of 3 or 4 different types of plastic and spread them on a filter. And, these instruments can deal with those types of samples very effectively. But you then prepare a real sample from some wastewater treatment plant or something like that, and it's much more messy, and the problems of identifying the particles accurately and then figuring out whether they're really plastic or not, that becomes much more complicated, shall we say. So the difference between the theoretical capability and the day-to-day reality is still quite large, I would say.
So what's being noticed about the structure of some of these microplastics once they're successfully separated from their water or air or whatever? What are some interesting things that have been discovered about the morphology, et cetera?
I don't know what you'd call interesting. Certainly, you can see surface cracking and crazing on plastics very easily in lots of aged microplastic samples. So if you, for instance, take a piece of polypropylene, if you look at a nice, new, clean piece of polypropylene fiber, it's got beautiful, smooth, shiny surface, perfectly cylindrical, probably. It just looks really elegant, smooth, perfect. You find one that's been kicking around in the environment for a few decades. Maybe it's been exposed to a lot of very strong UV radiation, and you see it looks like kind of rough tree bark on the surface. It's all crazed and cracked, and you can see all little fissures and breaks in it. And if you handle it, you can actually see it breaking up and little pieces peeling off the surface of it. So it really is quite like tree bark, actually, in a way it behaves.
Well, is it monolithically like tree bark, or is it like overlapping scales of material? Does it?
Yeah, well, it's a surface layer, and generally speaking, if you chip a few bits of the surface layer off, you can see the underneath of it, and the scales kind of chip off a little bit roughly. But it depends very much on the individual sample and what kind of environments it's been exposed to. So I don't think I could say anything really very, very general about that. We see all kinds of different things, different kind of surface damage, different kinds of crazing patterns according to what kind of polymer it is and where it's been and what its history is.
Okay. Well, very good, Andrew. What's the best way for people to find out more about your work? Where can they go?
I'd love to say they can go to my website. Unfortunately, my website is in a bit of disarray at the moment. We have quite a nice website at the university about all the work we've done in Malaysia, setting up the Malaysian Microplastics network. I have published quite a few papers, so people can go to the scientific literature. There's also there's blogs available on our website at the university about some other projects we've done, for instance, looking at the hidden plastic inside tea bags and the consequences of that. So we've done quite a lot of work in that area, and it's something that the public is often interested in because it's a really common everyday product that people handle and use. And typically they throw those, their tea bags. You think it's all paper and tea. It's just biological stuff. You throw it in your compost at home, but unfortunately the plastic components that are hidden inside those tea bags, they don't degrade very quickly. Some of them don't degrade at all. They're made out of polypropylene and they last for hundreds, maybe even thousands of years. We really don't know how long they're going to last. So people are finding these kind of skeletons in their compost heaps all the time from the plastic waste that's hidden in those products that they don't realize is there. And we're throwing all that stuff out into the environment, and gradually, it physically gets broken up into microplastics.
Oh, one last question I forgot to ask you. When you successfully separate, microplastics and analyze them, are you seeing mostly polymer backbone, or are you also seeing like a substantial number of additives and plasticizers and all kinds of stuff that they put into plastic to make it what it is?
In general, we identify them based on their kind of core plastic composition. So many of these materials probably do have additives. Certainly pigments, color additives, we see them quite a lot, and you can also detect them spectroscopically. Certain types of polymers, maybe you might see some of the plasticizers in them, because a few types of polymers like PVC, for instance, often have quite high levels of plasticizer in them. And depending on how long they've been in the environment, they might still contain quite a lot of that plasticizer. But the very sort of minor trace additives, we tend not to see them in our basic analysis because they're just present at too low concentrations. So if you want to study them, you really need to do quite serious extraction of the polymer fragments to deliberately extract those small molecules out and then analyze them by alternative, really sensitive techniques like gas chromatography, mass spectrometry, for instance, if you're interested in, flame retardants or something like that. So you won't see that in routine microplastic analysis to identify the plastics. If you're interested in that, you have to extract it and measure it in a different kind of way analytically.
Okay, understood.
It's certainly been done. There are actually some very interesting studies of nurdles, the small pellets that are manufactured as virgin plastic, and it's the way they're shipped all around the world from manufacturing sites to plastic production sites where they're melted and turned into the plastic objects we use and buy. But lots of those plastic pellets get spilled in the ocean, and they float around in the ocean, and they eventually wash up on beaches, and they act like kind of extractors. So they float around and they extract all the small molecule contaminants that are in the water around them. So if you collect those materials up off beaches and analyze them, you can actually find out about a lot of the small molecule toxins and contaminants that are present in the oceans, actually, at very low levels. And there's been quite a number of very interesting studies done on that, comparing the kind of the toxins that these plastic particles have picked up in various different parts of the world, depending where they washed up on the shore. So that it provides a kind of fascinating and slightly scary insight into all the trace chemical contaminants that are out in the ocean.
Do you know if anyone is working on techniques to separate microplastics from blood or from other bodily fluids like urine? I just saw an article saying that microplastics appear to be in some people's blood. That's why
there are. I haven't studied in detail exactly how they're doing those extractions, but they certainly have been doing them. And I imagine, again, it involves a level of digestion of the biological material to get rid of that and then see what you have left. But certainly they've been reported in blood. They've been found in various organs, larger animals. I believe the first evidence that microplastics may have crossed the placenta from mother to baby has been identified. So it certainly seems like, we know we're eating them, we're breathing them in, and a certain number of them seem to be crossing the kind of primary barriers through either through lung mucosa into the blood system or through your gut wall into the blood system. So that definitely seems to be happening, but I don't think there's any really good understanding yet to what extent that's happening and whether it's causing us serious harm or not.
It'd be interesting if you developed a protocol for, again, separating them from urine. Obviously it's a liquid. I don't know, it may be a very good clinical test for all kinds of applications in the future. It might be something to work on.
Yeah, I mean, it could be interesting. I'm not sure if they've been detected in urine, to be honest. And I'm thinking that, the kidney is a very good filtration mechanism. So if you did have particulates, that maybe the kidney would actually retain them rather than passing them.
Yeah, if you looked at, actually, that makes the, I know we're going down in kind of a rabbit hole, but, if you got, cadaver kidneys and looked in the glomerulus, and if you saw nanoplastics or microplastics kind of gumming it up, that might give you an idea if it's getting to that point.
I'm reasonably confident that somewhere in the world there's probably a number of studies going on in exactly that kind of direction, using various types of post-mortem and biopsy samples, for instance, from clinical studies or just, post-mortem materials. But it's not a world that I inhabit, and it's not something that I'm personally am involved in, but I am aware that there are groups doing that kind of work. And, it's an excellent place to look as a starting point, because you can't experiment on live humans very easily. So, if we really want to know what's going on in humans, that's our only access to information, really, in the first instance.
Okay. Well, I know you can't do everything. You're only one person. But
I'm one person. I have a relatively small group, so I need to focus on things that I think I understand and that I'm good at, and leave lots of other stuff to many other groups who are well resourced and well connected, maybe to the right medical groups who can give them access to those samples. So, there's lots and lots of people around the world researching microplastics by now, and a certain number of them are definitely focused in that direction. So I think in the next 2 or 3 years, you'll be seeing lots more data about their prevalence in humans and other mammals, and understanding how they get into us, how they get out of us, if they get out of us, and where they accumulate maybe in our bodies, which organs tend to accumulate them, what happens to them, do they cause any kind of issues?
Okay, well, very good. Andrew, it's been a great call, and I really appreciate speaking to you about this, and thank you for coming on the podcast.
Okay, well, it's been a great pleasure to talk to you, and thank you very much for having me.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.